Okay, good morning. This is Professor David Reyes. Okay, my topic for this session will be a continuation of my long video format topic on AC machines, and this will now be lesson number 27. Lesson number 27 is it will be an example problem on how to compute all the efficiency of transformers. Okay, don't worry guys. After this, we'll be discussing the parallel operation of transformers in real life. But before we will go with that topic, we'll try to bring out first another illustration problem for all the efficiency of transformers. It's another variation because the last time around we solved all the efficiency, but it was another type of problem. The requirement is still all the efficiency, but the given variables are different from here. So, okay, let's proceed for this morning. The topic will be alternating current machines, lesson number 27. We are running smooth. Okay, don't worry more guys. The boring time, if we are discussing concepts, it's a little bit boring, but that's actually the most important thing in the study of engineering. The study of concepts, okay? It's just a mind-twisting thing, Don't just concentrate on the problem solving. The important thing here is the concept. Okay, let's proceed. AC machines, lesson number 27. The title of the topic will be example problem on the computation of all the efficiency of transformers. Okay, I will try to read the problem for this morning. The resistances of a 500 kVA transformer with the voltage specification of 11,000/2300 volts, frequency 60 Hz, are respectively 0.8 ohm and 0.04 ohm for the high and low voltage sides. What is given is the resistances for both the primary side and secondary side. That's why it says here high and low voltage side. High refers to primary, low refers to the secondary, meaning the resistance of the windings on the primary side is 0.8 ohms, and on the secondary side it is 0.04 ohms. Okay? Letter A. The iron losses is 3000 watts. Calculate the full load copper losses. So the number one requirement is the full load copper losses. Full load. If it says full load, the given power rating is 500 kVA, right? So the full load rating is actually 500 kVA. So the problem is asking what will be the value of the full load copper losses. It specifies full load, so in the computation of the current, we will take the full load apparent power. Letter B. This transformer is loaded daily as follows: 2 hours at full load, 3 hours at 3/4 full load, 6 hours at 1/4 full load, and the problem is asking calculate the all-day efficiency. Right? All-day efficiency. Why did the problem ask for the full load copper losses? The problem specifies that we must have to compute for the full load copper losses because in the computation of the efficiency we needed this one. And maybe the problem is just testing us if we know how to compute copper losses if we are given the resistances. Because the last time around, the copper losses are not in terms of the resistances. It was actually determined by using the short circuit test for the transformer. So actually the last problem was different from tonight, but still the requirement is on the efficiency. Okay, let's try to bring out the givens. We specify the given, so when we go to the calculation, we'll just go back to the numbers placed on the given, right? You don't have to go back anymore toward the verbal problem. The total apparent power is 500 kVA. Capital letter S is the designation for the total apparent power for transformers or AC circuits. The voltage specification is 11,000 slash 2,300. Primary is 11,000. Secondary is 2,300. Frequency is 60 Hz. Okay. Frequency of the primary is the same as the frequency of the secondary. 60 Hz. Right? Small letter r with the subscript p, meaning the resistance of the windings referred to the primary is 0.8 ohms. Small letter r with the subscript s is the value of the resistance referred to the secondary. It is 0.04 ohms. The iron losses is 3,000 watts, or if we divide this by 1,000, this is actually 3 kilowatts. Okay? And the problem is asking what will be the full load copper losses and the all-day efficiency with the different types of loading. It is this: 2 hours, 3 hours, and 6 hours, 2 hours at full load, 3 hours at 3/4 full load, and 6 hours at 1/4 full load. Okay, let's try to bring out the solution. Full load copper losses, what do you call this? Power is equal to I square R, right? So if we try to compute for the true power, we will place the subscript here, copper losses. Okay? So we must have to compute for the current times the value of the resistance. The resistance is actually given, but we must have to compute for the individual current to compute for the copper losses. So actually here, full load copper losses is the copper losses, okay, with the subscript P, meaning on the primary side, plus the copper losses with the subscript secondary side. And the formula on how to compute for the copper loss is actually the square of the current times resistance, square of the current times resistance. On the primary side, it should be the square of the primary current times the resistance referred to the primary, plus the square of the secondary current times the resistance referred to the secondary. We are given R sub P and R sub S. They are both, this is 0.8 and this is 0.04. So the only problem now to compute for the copper losses is to compute for the primary current and for the secondary current. The primary current will be kVA, the apparent power, multiplied by 1,000 over the voltage on the primary. We got this equation from the equation volt ampere is actually equal to the product of EI, right? Sorry for that one. Volt ampere. So if we try to compute for I, it should be volt ampere over E. Right? It is this. The given and apparent power is kVA, so we must have to convert it to VA. Okay? So there is a multiplier 1,000 over here. So substituting value, the full load primary current is 500 kVA. We multiply this by 1,000, so this will now be volt ampere. All over 18,000 volts, this is volts. Right? So volts and volts cancel. So the unit of this is actually ampere. It's current. So this is 500 times 1,000 over 11,000. And this is 45.45 amperes. So this primary current here is 45.45 amperes. Computing for the secondary current, we will use still the same formula. 500 times 1,000. The voltage on the secondary side is 2,300. This is over 2,300. Secondary current will be 217.4 amperes. It is bigger. Why it is bigger? It is bigger because the transformer is stepped down. It will be something like this: high voltage, low current, low voltage, high current. Okay? So for these two things to be equal, if this is high, this should be low, and if this is low, this should be high. That's why the secondary current is bigger than the primary current. It is a step down current. Right? So going back to this formula here, it will be 45.45 quantity square, the primary current, times 0.8. Okay, the resistance of the winding on the primary side is 0.8. We multiply that by the square of the primary current. That's the total copper losses on the primary side. The current on the secondary is 217.4 quantity square. The resistance on the secondary is 0.04. Taking the summation of this, it is 3543 watts. Converting this to kilowatts, we divide this by 1000, or actually you could place it in 1 kilowatt per 1000 watts. So watts cancels. What remains for the unit will be kilowatts, but we must have to divide this by 1000. So this is 3.543 kilowatts. Oh, that's the answer for number 1, the full load copper losses. Full load is 500 kVA. So the currents are actually based on the full load value of 500 kVA. Letter B. We are just given the apparent power, but for the loadings, the problem didn't specify the power factor. So to be on the safe side, we will assume that the power factor is unity or 1. So I place it here, assume power factor is equal to 1. Okay, for all load conditions. Meaning, at full load, 3/4 full load and 1/4 full load, we use a power factor equal to 1 to be on the safe side. Because it was not given. Right? Okay, let's try to bring out the output kilowatt hour. The output of these loads. Kilowatt hour is actually the product of kilowatts times hour. Right? This is full load, right? Okay? The first one is full load. The total true power, if the power factor is unity, is 500 times 1. Right? How many hours it is operated? It is 2 hours. So this is kilowatt times 2, it's kilowatt hour. Kilowatt hour, it's energy. Next one is 3/4 full load. This is 3/4 full load. The load for the first one is full load for 500 kVA times 1. Next one is 3/4 full load. So we will multiply this by 3/4. Okay? The true power is actually 500 times 1. This is kVA times 1. Apparent power times power factor is true power. But at 3/4 full load, we need to multiply that by 3/4. How many hours it was operated at 3/4 full load? It's 3. Right? Next one. It is only 1/4 full load. So there is a multiplier 1/4 here. The true power is 500 times 1. Meaning the load at that one is only 1/4 of 500 times 1. Multiplied by 6, it was operated for 6 hours. So this is multiplied by 6. Taking the summation of this by using our calculator, it is 2875 kilowatt hour. This is small compared to because this is 500 kVA, right? Okay, let's try to compute for the kilowatt hour losses. Kilowatt hour losses is the losses due to the what do you call this, copper losses. The last time around, I gave you copper losses is equal to N square times the full load copper loss, right? There is an n here, we must have to square that one. That's why I derived the formula for the computation of the copper losses in terms of the nth loading, right? So, for number 1, it should be 1 square. At full load, n is equal to 1, right? So, this is 1 square. The total copper loss is actually 3.543. Where is it? Right? How many hours it was operated? Times 2. So, kilowatt times hour, it's kilowatt hour, right? But it's losses. Next one. The value of n for the next one is 3/4, right? So, this is 3/4 square. By using this formula, right? Times the copper loss, full load is 3.543. How many hours it was operated at these losses? It's 3 hours. 3 hours. So, this is multiplied by 3. Next one, plus. The last part is only 1/4 full load. So, the value of n is 1/4, but we must have to square that one. Okay? Times the full load copper loss, right? Times 6 hours. So, we are done with the copper losses at the 3 given load conditions. The first one is full load. Next one is 3/4 full load. Next one is 1/4 full load. But in the copper losses, this should be squared, okay, by using this formula here, right? What's the last part of the losses? It's the core loss. Core loss is actually 3K, 3,000 watts of 3K. So this is kilowatts, 3 kilowatts, right? For the core loss, whether the transformer is without load or without no load, right? The core loss actually is present, so the multiplier should be 24. It is present for 24 hours. If there is no load, there is a core loss. If there is load, there is still a core loss. So this core loss here actually is present for a total time of 24 hours. Right? So taking the summation of this by using the calculator, 86.39 kilowatt hour. Okay, the total input kilowatt hour now will be the output plus kilowatt losses. So we add this one. What comes out is 2961.39 kilowatt hour. It is only due to this loading here. Right? And all the efficiency is output over input energy. 2875, the output is 2875, right? And the input is 2961.39. 2875 divided by 2961.39 times 100%. All the efficiency is 97.08%. Okay, that's it, guys. That's the way how to solve all the efficiency. If we are given the resistance to the primary, we are given the resistance to the secondary. So to compute for the copper losses, we will use the formula power is equal to I square R. Okay? So for this problem, we use this formula and how to compute for the copper losses. The last problem, the copper losses was actually given by using the short circuit test. So actually these two problems are actually different problems. But the requirement is still, we are asked to find for all the efficiency. Okay, good morning from Los Angeles. This is Professor DavidJDelosReyes. The next time around, we will be discussing parallel operation of transformers. Good morning from Los Angeles.